Let's look at this example. Find the general solution to the following differential equation, then find the particular solution using the given boundary condition. dy dx equals y divided by x squared. Y of 3 equals 1. We can separate this since the y and x squared can be considered multiplied together. And then I can move the y to the dy side by dividing by y or multiplying by the reciprocal 1 over y. I can move the dx to the other side by multiplying by dx. So I have 1 over x squared times dx. Now to prepare to integrate, I do keep this as 1 over y times dy, but any other power that's not 1, I bring it up and write it with a negative exponent, x to the negative 2. Now I'm ready to take the integral of both sides. On the left side, the integral of 1 over y is the natural log of the absolute value of y. On the right side, I get negative 1 over x plus c, my collective constant from both sides. Now this is a general solution. So I have done the first part and found the general solution. Now we're going to find the particular solution using the boundary condition y of 3 equals 1. So for y of 3 equals 1, that means the y is 1, so I plug 1 in for the y, natural log of 1. I don't need the absolute values because it's already positive. And 3 in for x, negative 1/3 plus c. Natural log of 1 is 0, so 0 equals negative 1/3 plus c, and therefore c equals 1/3. I plug this back into my general solution, and I can write natural log of the absolute value of y equals negative 1 over x plus 1/3. And now I have a particular solution. Technically, I'm done with this problem, but it's important to explore different ways that you could see or could write the solutions. So for the particular solution, we can do a lot with this because of the natural log, and we can even solve for y. If I have the natural log over here, to get the y by itself, I can exponentiate both sides. So I could rewrite this as e to the natural log of absolute value of y equals e to the negative 1 over x plus 1/3. That's another version of the particular solution, but using my log and exponential properties, those are inverses, so I end up with the absolute value of y equals e to the negative 1 over x plus 1/3. And then, because of the fact that y of 3 equals positive 1, that is greater than 0, instead of writing the absolute value of y, because y has to be positive, I can take away the absolute values and just have positive y, which equals e to the negative 1 over x plus 1/3. Still another form, but I can even do more. When I'm adding the exponents, it's the same as writing this as multiplying e to the negative 1 over x times e to the 1/3. Also, you often tend to see the constant expression in front of the algebraic expression, so we might also see this as e to the 1/3 times e to the negative 1 over x. Lots of different forms, all of these still particular solutions. There are also ways to rearrange the general solution if we needed to solve for y. Let's look at how we can do that. If I exponentiate from here without finding the c first, it looks like this. E to the natural log of the absolute value of y equals e to the negative 1 over x plus c. Very much like what we had in the particular solution. Now I can cross out because of the inverse properties, and I am left with absolute value of y equals e to the negative 1 over x plus c, which of course is the same as, just like we did here, e to the negative 1 over x times e to the c. If I take away the absolute values in this instance, I do have to consider that what I have is positive or negative. It could be either. So I have plus or minus. I'm going to put my constant term in front, e to the c times e to the negative 1 over x. Now, an easier way to write this is if I think about the fact that this constant, I'm going to call this constant c sub 1, is involved in this expression where we have plus or minus e, which is a constant, raised to another constant. So instead, I can collectively call that also just a constant c sub 2. So I could rewrite this as y equals a constant c sub 2 times e to the negative 1 over x. Essentially, the same thing that we had here, where it was a constant times e to the negative 1 over x. The point is, there are lots of ways that you could write a general solution as long as it has a plus c, and lots of ways you can write the particular solution as long as there's no c, which is the value you got from using the boundary condition. Let's take a look at another example. If dv dt equals negative 2v minus 32, and if v of 0 equals negative 50, then when t equals 2, v equals what? Let's start by solving this differential equation. Notice that this side has dv and this side has v. So we're going to move this v expression to the other side. But first, it would be easier if we don't have to take over too many constants. So let's see if I can factor this, which of course I can. dv dt equals negative 2 times v plus 16. Now I don't have to do it this way, but it's going to make it easier if I don't have to take as much over to the dv side, and I can leave a little bit on the dt side. So dividing by v plus 16, or multiplying by its reciprocal, I get 1 over v plus 16 dv equals negative 2 multiplying by dt times dt. Now I'm ready to do the integral or antiderivative of both sides. Because this is v to the first, antiderivative gives me natural log of absolute value of v plus 16, and this antiderivative, negative 2t plus c. I have a general solution, but I was given a boundary condition, v of 0 equals negative 50. I'm going to use the fact that v of 0 equals negative 50 to find a particular solution in order to answer the later question. V is negative 50, so natural log of negative 50 plus 16, I've plugged in negative 50 for v, equals negative 2 times 0 plus c. Doing a little bit of simplifying, that's 0. This is negative 34, so the natural log of the absolute value of negative 34 equals c, or rather, the natural log of 34 equals c. I can rewrite then my general solution into the particular solution. Natural log of absolute value of v plus 16 equals negative 2t plus natural log of 34. Now I have a particular solution that I can use to answer the question about what is v when t equals 2. Taking my equation from here, natural log of absolute value of v plus 16 equals negative 2 times 2 plus natural log of 34, where I took my particular solution and I plugged in the value for t that they gave me. Now I can simplify over here, so I have natural log of absolute value of v plus 16 equals negative 4 plus natural log of 34. We need to figure out what v equals, which means we need to solve for v. So to get the natural log to go away, I exponentiate both sides. Base e with all of that the exponent, base e with all of that the exponent, leaves me with absolute value of v plus 16 equals e to the negative 4 plus natural log of 34. I can do a little bit of simplifying on this side because I remember that in my exponential properties, this is the same as saying e to the negative 4 times e to the natural log of 34 since I'm adding those exponents. Then using my inverse properties, e and natural log are inverses, and I can bring down the 34. So now I have the absolute value of v plus 16 equals 34 times e to the negative 4. Now I'm going to remove these absolute values, and to do that, I want to remember that v is negative when I plugged in that boundary condition. So when I take away the absolute values, v plus 16, I have to have a negative result, negative 34 e to the negative 4. Finally, subtract 16 from both sides, and v equals the value negative 34 e to the negative 4 minus 16. Thanks for watching.